So, welcome to session 3 on pharmaceutical development, part 1. The contents of this session is we're going to first look at the concept of pre-formulation. Okay, I'll just get my little laser pointer here. Yeah, okay. We're also going to look at pre-formulation studies. Something that's very important for these studies is investigating solubility and distillation rate. Also, stability of compound is also required, and this is information that will help us to kind of understand how chemicals or compounds react in the body. Particle size. So particle size is actually quite critical in drug discovery. So the smaller the particle, often the better it is, but not always necessarily true. Also the morphology of the particles, which they will kind of investigate what different types of compounds and how their kind of crystal structure, which will kind of alter how they're absorbed. Also the routes and administration and dosage forms. We're also going to look at formulation, so things like fillers and capsule formulation. This is kind of a big area of kind of the drug discovery. We're also going to be looking at principles of drug delivery systems, so what types of polymers and micelles are used. A big area, a hot topic, is nanotechnology and nanoparticles. It's thought that this part of drug discovery is going to kind of take off, and it has already started to. What's also interesting is to kind of slow down the release of drugs, so having modified drug release. And also drug delivery to the central nervous system. So how many drug forms are there? Well, there are many different forms. So we've got things like emulsions. You might have seen, for example, kaolin morphine is like an emulsion. Some drugs come as like capsules or as powders, which are kind of dissolvable in water or in juice. We also have aerosol sprays. So in the case of kind of if you've got asthma, maybe herbal teas, creams, tincture, medical herbs. So in the case of kind of Chinese medicine, these are quite popular. Sprays, suspensions, all sorts of shapes and sizes, even gels and patches. Okay, so there's all sorts of different types. The pre-formulation testing is the first step in the rational development of dosage forms. This involves developing a dosage form, and it's having kind of physical and chemical properties of the drug. It's actually defined as an investigation of the physical and chemical property of the drug substance alone, and also when combined with something called excipients. So these are the kind of things that we add to the drug capsule. Most synthetic drugs are weak bases, so around about 75%, but also there are weak acids, so about 20%. They're normally formed as salts, which will actually change the chemical property and drug response. The physicochemical properties are those that can be determined normally from in vitro experiments. So normally the first kind of pre-formulation steps are performed in vitro. So the concept of pre-formulation is that all drugs that are marketed as tablets, capsules, or both, prior to the development of these major dosage forms, it's essential to have certain fundamental physical and chemical properties of the drug molecule and other properties of the drug powder that are determined. So the information decides many of the subsequent events and approaches in the formulation development. So here's this wonderful picture. It looks like, these look kind of very edible, don't they? Look like sweets. But you can see that the capsules come in all sorts of sizes. And what we'll look in the online session is I'll show you and you'll be able to see them live. You can see different types of capsules and how they actually kind of put together. The concept of pre-formulation, The first learning kind of phase is known as this pre-formulation. So, and the definition is that it can be defined as an investigation of the physical chemical property of the drug, as we've already seen. The overall objective of the pre-formulation testing is to generate information useful to the formulator in developing stable and safe dosage forms with a good bioavailability. So during the early development of a new drug, so the synthetic chemists will maybe working alone or with other people who are expertise in the field and also in other disciplines. They may record some data which can be then appropriately considered as pre-formulation data. So this early data collection may include information such as the gross size, particle size, the melting point, the infrared spectra, so this is the infrared analysis. We also can do thin layer chromatography, which you've probably done before, and other kind of characteristics. So this data is useful for guiding and becoming part of the main body of pre-formulation work. So there are a number of steps involved. So first, if we look at the stability, we're looking at the solid state. So this may be affected by things like temperature, light, humidity. Also the solution, so if it's in solution, it's also bear in mind what solvent to use. Some compounds are only soluble. Most compounds are normally dissolved in like dimethyl, but that's fairly toxic. So maybe that it needs to be water soluble. Also pH will change, and also light as well. So light exposure may change the compound. Also the physical chemical properties, so things like the molecular structure, the weight, the colour. So often if you've got a tablet and it's like a brown colour, it might be a bit off-putting. Also the odour, the smell. So it might be the smell is not good, and so you need to think about the smell. The particle size, okay, so that will kind of is really important, because the smaller it is, maybe can pass through kind of blood-brain barrier, for example. The shape and the crystallinity, which we'll look at in a moment. The melting point is also important, and the thermal analysis profile, so through something called DTA, DSC, and TGA. The hygroscopicity potential, and also absorbance spectra, so things like UV or infrared. The solubility can be checked looking in water or dissolved in other solvents like alcohol. The pH solubility profile is checked. Different salt forms are looked at, even co-solvents and something called complexation, and also the prodrug. And then there's also some calculations to kind of consider, so something called partition coefficient and also polymorphism potential. And the third part is the physical mechanical properties, so things like bulk and tap density, and whether or not, if it's like a fine powder, can it be compressed into a tablet. Something to bear in mind, in vitro availability properties, so whether or not there's things like something called dissolution of the drug crystal per second, dissolution of the pure drug pellet, and dissolution analysis of pure drug. And other studies are things like plasma protein binding, the effect of compatible excipients on dissolution, and kinetic studies of solution degradation. So bear in mind like the physical chemical properties, so the particle size, shape, surface area. So various chemical and physical properties of a drug are affected by the particle size, distribution, and shape. And this is not only on the physical property of the drug, but also in some instances on the biopharmaceutical behaviour. And so it's actually generally recognised that poorly soluble drugs showing a dissolution rate limit step in absorption process will be more readily available when administered in a finely subdivided state rather than as a coarse material. So in the case of tablets, and size and shape influence the flow and and the mixing of the powders. So when they're manufacturing the powders, if it's a very fine powder, it may you may lose a lot of the product in the factory. Also, the size can affect be a factor in the stability, and also fine materials are more open to attack from the air, so atmospheric oxygen, also humidity, and interacting with excipients more so than are the coarse materials. So the effect of particle size and shape on the chemical and physical properties of drug substances. So we've got things like bioavailability of drug substances, which we'll kind of have a look at later. The flow and mixing efficiency of powders and granules, so making the tablets, and also the stability. So we've already kind of looked at this already. So very fine materials are difficult to handle, and you can overcome by creating something called a solid solution in a carrier. So this is like a water-soluble polymer. However, you need to decide and maintain and control this desired size range. So the safest way is to grind most new drugs with a particle diameter of about less than 100 millimeter. And they use something called like a mesh, so a mesh of 140. And then the smaller the size, the larger the mesh. So down to 10 to 40 millimeter. Particles with a diameter of less than 30 millimeters, grinding is actually unnecessary. But except if you get some like needle-like crystals, which will help to improve the flow and stop the blocking of the mesh. The drawbacks of grinding is that there are material loss. There's also a build-up of static, and so essentially this is what's going to happen. So yeah, build-up of static, and all the particles will kind of flow up into the air. So something called aggregation. So this is like lowering of distillation rate, and also polymorphic and chemical transformations. There are general techniques for determining particle size. The particle size can be determined through kind of microscope, so through optical microscope, so using a polarized microscope, for example, or more fancy microscope is a scanning electron microscope. The data recorded either by is then drawn, or you can take a picture. So if you're using the microscope, you might have a camera, you take a picture. Or if you're using a scanning electron microscope, you can take a picture through the computer. The polarizing microscope, this is used to determine whether a compound is crystalline or amorphous. The crystalline structures are visible, so they tend to refract the polarized light, whilst the amorphous are actually invisible. So microscopy is actually the most rapid technique. It doesn't require too much expertise. Whilst the kind of like scanning electron microscope it requires a lot of expertise, it's expensive, and you have to prepare your sample, and also you have to spray it with a metal like with gold. So it's quite an expensive technique. But for quantitative size determination, it requires kind of counting large number of particles, so it's not always the kind of best method. So even suspending the particle in a non-dissolving fluid, so water or mineral oil, we can then use other methods to count, which we'll explore after. So the crystal habit or internal structure of a drug can affect the bulk and physical chemical properties, which range from flowability to stability. So the habit is a description of the outer appearance of the crystal, where the internal structure is the molecular arrangement within the solid. So we've got different types. So we've got, for example, we've got the tabular, okay? So that has a moderate expansion of 2 parallel faces. We've got the plate form, the prismatic form, and also these are acicular. So these are needle-like structures, and also the bladed form. So these are kind of flattened needle-like structures. The internal structure of the compound, so this is the major distinction. is whether the solid is crystalline or amorphous. Okay. Another thing to bear in mind is the melting point. So the melting point is defined as the temperature at which the solids and lipid phases are in equilibrium, so it's when it melts, and it can be measured using 3 techniques. So we've got the capillary melting temperature, so we use like these special capillary tubes, and we have it in a heat block, and then we measure at the temperature that it the liquid starts then to move up through the tube. That means like the temperature of melting. There's also something called hot stage microscopy, so that's obviously visualizing through the microscope and watching for the temperature, looking at the temperature of melting. Also differential scanning colorimetric or thermal analysis. The capillary method, this gives information of the melting range, but it's quite different to assign an accurate melting point. The hot stage, this is a visual observation. Often you're equipped with a heated or lag stage, and the heating rate is controllable up to 3 transitions that can be registered. So these values are actually more accurate. The differential scanning, colorimetric, and thermal analysis, I think these are probably the best methods. So the DTA, that measures temperature difference between sample and a reference as a function of the temperature or time when heating at a constant rate. Whilst the differential scanning colorimetric DSC is similar to the DTA, except that the instrument measures the amount of energy required to keep the sample at the same temperature as the reference, so slightly different. These are more accurate ways of measuring the melting points of compounds. The thermal analytical profile, so DSC and DTA, these measure the heat loss or gain resulting from the physical chemical changes within a sample as a function of temperature. And examples of that are things like endothermic, so heat absorbing process. So we've got like fusion, so even have like boiling, sublimation, vaporization, solid transitions, and chemical degradation. Exothermic process are kind of crystallization or degradation. So here we can see this is actually a profile, so it's called the DSC, thermal profile of something called aceclopher, which is a pure form. So here's there's a peak here, it's about 250, and the first peak, which is for ethyl cellulose film. So these are pure substances, okay, so this is a kind of a typical profile that we'd see. Now, if we take the same compounds and we mix them and they're not so pure, what we see when we look at the thermal profile is that it changes. So the ethyl cellulose film, it's quite similar, but you don't see this slight peak here. There is a peak here, but it's very different, okay, it's much more shallower. And then also this peak here, you can see that's kind of disappeared a little bit. It's not as clean. So, and that's because this sample is a ethyl cellulose film containing 12.8%, so it's not a pure solution. And also there are other things in here which we call the excipients, so 15% propylene glycol and 10% tween. So it changes the profile, so that's something to bear in mind if you're not working with a pure substance. So we need to accurately, quantitatively determine different aspects about a drug. So this is just kind of a sequence of measurements. So how we do that. So we start off with an excess drug powder, normally about 150 mg per ml, so 15% plus the solvent. We add this to an ampule vial with a volume of 2 to 5 ml. It is then shaken then at a constant temperature, either at 25 degrees or 37 degrees, or it's between 2 and 8 degrees. Now that's done for 48 hours. After 48 hours, there is a kind of filtration. So the first few mils are filtrated, should be discarded due to possible filter absorption. So whereas they're filtered through this membrane filter of 0.45 micron, afterwards you can determine the concentration in the filtrate. Then again, you're you're waiting then 72 hours, you filter again through the 0.245 to determine the drug concentration and filter rate. And then later than 72 hours, again filter. And then we look, compare the same concentration and look at the solubility of our compound. Something also to bear in mind is the pKa determination. Now, we've looked at this before, and I won't spend too much on this slide, but this is based on the Henderson-Hasselbalch equation. So for acidic compounds, we have a pH which equals pKa plus log of the ionized drug divided by the unionized drug, whilst for basic compounds, it's a pH which equals to pKa plus the log of the unionized drug over the ionized drug. So to kind of summarize, for a weakly acidic drug with a pKa value greater than 3, the ionized form is present within the acidic contents of the stomach. So that's something that we need to bear in mind when we're kind of giving drugs. So if you're giving a drug as a pill, sometimes some drugs, the drug's not is preferred to be given like with the food or prior to the food, and that will depend on the whether or not it needs to the acidity of the stomach. But the drug has to be ionized in a neutral media of the intestine. For basic drugs such as erythromycin or papaverine, the pKa is between 8 and 9, and the ionized form is a predominant in both the stomach and the intestine. And so there's a buffer in temperature and ionic strength and co-solvent effect on the pKa value. Also, the partition coefficient, so this is the oil-water coefficient. So it's a measure of the drug's lipophilicity, and it's an indication of the ability to cross the cell membrane. So something to bear in mind. It is determined as a ratio of the unionized drug distributed between the organic and aqueous phases at equilibrium. So the partial coefficient in oil and water equals the coefficient of oil over the coefficient of water equilibrium. So the partition coefficient can provide like an empiric handle in screening for some biological properties. So for drug delivery, the lipophilic or hydrophilic balance has been shown to be a contributing factor for the rate and extent of drug absorption. The partition coefficient data alone actually doesn't provide us enough understanding. It provides a means of characterizing the lipophilic and hydrophilic nature of a drug, but the biological membranes are lipoid in nature, so the rate of drug transfer, which passively absorb drugs, are directly related to the lipophilicity of the molecule. The partition coefficient is commonly determined using the oil phase of something called oxanol or chloroform and water. And drugs having values of P much greater than 1 are classified as lipophilic, whereas those of coefficient less than 1 are indicative of hydrophilic drug. Okay, so pH solubility profile. How would you do this? So how would you go about checking the pH solubility profile? So you can stop the video at this point, okay, and have a go at trying to figure out how. So if you take excess of drug, how would you test that? Okay, so if you had a go, this is the answer. Okay, so first you would take your excess drug powder. You would then stir in a beaker with distilled water. Afterwards, you would then continuously stirring of suspension. You would add acid or base, and then stir, and then measure the pH of the suspension. Okay. Then afterwards we would filter like we did before, and then we can determine the concentration of the drug in the filtrate, and this will give us the solubility. So here we'd get the pH and the solubility profile of our drug. Okay. Okay, so the pre-formulation studies, so the development of the solubility spectroscopic assay method for determining concentration and purity. The determination of solubility and distillation rates of the parent compound in salts and in water and other solvents, and the chemical stability of parent compound or salts in solution and solid state. The determination of pKa and pH is dependent on the solubility and chemical stability, and the determination of lipophilicity, the oil-water partition coefficient, that's expressed as Kd. We've also got the determination of particle morphology and melting point and suitability for milling. Okay, so remember the particle size is quite critical for that. If you have a fine powder, then you may get a lot of dust and you may lose your product. It's not ideal when you're trying to prepare your compounds for encapsulation. The characterization of importance for the dosage forms of choice, so bulk density, powder flow, angle of repose, and compression properties are all kind of important for the pre-formulation studies. So solubility and distillation rates. So this is measured using UV visible spectrometry, or something called a nephelometer, which involves determination of a concentration of compounds in solution after equilibration. And this is when you stare for like several hours from pure solid. So most compounds have solubility of around 10 mg per ml, and they have no problems for formulation. A typical device looks like this. So this one's made by BD Bioscience. Compounds with less than 10 mg per ml need to be converted to salts, or you add a non-aqueous solvent for efficient oral absorption. Also, if you've got extreme pH values, these may cause some damage to tissue, so that's not ideal. And so the addition of solvents such as PEG, so this is polyethylene glycol, that's necessary for injectable drugs. There may be complications of the oral formulation, so if solubility is dependent upon pH, so there's large differences between the stomach and intestine. So for example, the gastric has a pH of 7 when there's no food. When there is food, there's a pH of 1 to 2. The intestinal pH always stays at pH 8. So basic compounds will dissolve really well in the stomach, but could actually precipitate in the intestine, so fail to be absorbed. Compounds present as more than one crystal form may be more complex and display a different behaviour. And also the lattice energy of the two crystal forms has different solubility states, which could actually promote the precipitation. And so selecting the best salt form and testing is then required. Okay, so determination of solubility. So this is a semi-quantitative determination. So let the video just finish. Okay, good. So the solvent, so this is a fixed volume. We add solute in small volumes, incremental amounts. So, and this is done kind of with a vigorous shake. And then you examine visually. So you then search for like any undissolved solute particles. If you still have some undissolved solute particles, no. Okay, so we keep on adding more solute. Okay, until eventually, if it's all dissolved, we say yes, okay, and then we work out the total amount is added up, and then you can estimate the solubility. The United States Pharmaceutical has a solubility classification. So this is kind of very random, I feel. They use descriptive terms, but also they use parts per solution or something. So they have anything from very soluble to freely soluble, down to sparingly soluble, slightly soluble, very slightly, or practically insoluble. This is a very, very random way of describing things like this. But then parts of solute required for one part in solute, so less than 1. So this is more kind of like a numeric value is more appropriate, I think, up to anything like 10,000 and over. There are common solvents that are used for solubility determination. So for example, water, polyethylene glycol, so that's PEG, propylene glycol, glycerin, sorbitol, ethyl alcohol, methanol, benzyl alcohol, isopropanol alcohol, and tweens. There are also polysorbates and certain oils, so things like castor oil, peanut oil, sesame oil. Obviously, there's probably implications of using peanut oil if people have got allergies, so those are probably not always ideal. And also having a buffer at various pHs may help with solubility. Anyway, that's the end of the first session. We'll now move on to the second session.